In this video, we're just going to review some of the concepts of a limit from the beginning of this course. So first, where does the limit not exist? Well, remember, a limit doesn't exist where you're not approaching the same point from both the left and the right. So like here, even though there's a hole in the graph, you're approaching that y value of 0 from both sides. So the limit exists here. Where the limit doesn't exist is at 1, because we have this jump discontinuity, right? It's approaching 2 from one side and 4 from the other. And at x equals 5, because we're approaching 3 from one side and 1 from the other. So the limit does not exist at x equals 1 and x equals 5. All right, now the function's values. Well, f of negative 1, the function's value at negative 1 is negative 1. The function's value at 1 is 2. The function's value at 5 is 3. All right, now, so that's just values. Now let's do the limits. The limit as x approaches negative 1. Well, as you approach negative 1 from both sides, you're approaching 0. So that is our limit. Now, this right here is what's called a removable discontinuity. And the reason it's removable is because that is the one and only type of discontinuity where the limit actually exists. The only problem is the limit is not the same as the function's value. To be continuous, these two answers right here would need to agree. Okay? The function's value and the function's limit, if those are the same, then it's continuous. And I know we're not talking about continuity, but it's just worth mentioning. All right, the limit as we approach 1 from the negative side. So we're approaching 1 from the negative side. We're approaching a y value of 2. Approaching 1 from the positive side, well, we're approaching a y value of 5. It doesn't matter that there's an open circle there. It's just what we're approaching. Approaching 5 from the negative side. Well, from the negative side, we're approaching a y value of 3. And from the positive side, we're approaching a y value of 1. Now in this, we're just going to start with trying to algebraically do some limits. I'm going to actually start with this one, the second one, because the first thing we should always try and do is just plug in the number, right? 4 times 4 minus 3 is 13. 3 times 4 minus 1 is 11. So the limit here is 143. You can see the next one down if I just plug in 2. 5 multiplied by 2 cubes, so 5 multiplied by 8 is 40. The next one down, 2 multiplied by 4 minus 6 is 2. And what you'll find, a lot of limits can be evaluated by just plugging the number in. Now, of course, on an AP exam, they're not going to be this easy. But what this means that I could just plug it in is that the function is continuous because the limit's value is the same as the function's value. Well, let's look at one where that doesn't work. Okay. If I plug in negative 1, probably the first thing you see is, this is going to be 0. That does not mean the limit doesn't exist there. We also need to check the top. So negative 1 squared, so 1 minus 3 plus 2 is also 0. So I'm going to make a little note here. I get 0 over 0. This is what's called an indeterminate form, which means I need to do a little more work. If I had gotten 5 over 0, there was no limit exists. If I'd gotten 0 over 5, the limit's 0. But here, when I get 0 over 0, I have to do more work. So let me do a little factoring. Okay, the top would factor to be x plus 1 and x plus 2. Okay, and let me just kind of cross that out. So the x plus 1 divided by x plus 1 is 0. Or I'm sorry, it's 1. Now I plug in negative 1. Again, I try it again. Negative 1 plus 2 is 1. That is the limit. Now, what that means graphically is that there's a hole in the graph there. So even though if I just sketched it, even though the limit exists, the function's value does not, so it looks like this. Okay? All right, going down to the next one. Actually, let's go over. If I plug in -5 here, of course, 0 on the bottom, but you got to check the top. 25 minus 40 plus 15, I do get 0 over 0. So I factor. This would factor to be x plus 5 and x plus 3. The x plus 5s divide out. Try again. Plug in -5. -5 plus 3 is -2. Okay? I'm going to do a couple more that look like this, okay? And then we'll go back to these kind of weird sign ones. So like down on this one, on the bottom, if I plug in 0, I get 0 over 0. So if I factored an x out of the top and bottom, let me just kind of do this with some shorthand that cancel out. Now I try and plug in 0 again. 2 times 0 minus 6 divided by 3 is -2. Okay, coming up here, if I plug in 3, I get 0 on the top. I also will get 0 on the bottom. So I could do a little factoring. Of course, x plus 3 and x minus 3. X minus 3 and x minus 7. And cancel out the stuff in common. Now I try and plug in 3 again. I get 6 on the top, -4 on the bottom. 6 divided by -4 is -3 halves. This next one, if I plug in 2, well, 3 times 8 is 24, minus 8 is 16. The bottom is 3. No extra work needed. Just plugging it in, it's 16/3. This next one down, if I plug in 0, I'm going to get 0 on the top and 0 on the bottom. So think about factoring an x out of every single term. So I make this x squared, this just x, and this just 10. Cancel with this 1 on the bottom. Plug in 0 again, and I'm just going to get 10. Last one on the bottom here, I plug in 2, I get 5 times 8 over 2 times 2, so 40 over 4 is 10. All right, let's do these last two. One thing to remember is that the limit as x approaches 0 of sine of x over x is 1. And that's always true as long as, I'm going to run out of room here, as the coefficients are the same. If it was 2x over 2x, well, it's not. And I'm not allowed to just multiply the bottom by 2 unless I do that to the top as well. So what's inside here, the limit is 1, but of course it's 2 multiplied by 1, so the limit is 2. And this other one, up here, again, I need them to be the same. So if I multiplied, I can't really multiply into the sine function, but I can multiply this by 1/2. I have to do that to the top as well. So now, of course, it would be 4x, sine of 4x over 4x. So that would be 1/2 multiplied by 1 is 1/2.